Welcome back to linear algebra. In this video, we're going to be revisiting the idea of a linear transformation. We've seen previously how linear transformations work in the Euclidean vector spaces. Now that we've expanded our roster to more generalize the idea of what a vector space is, we're going to take the same idea of linear transformation and generalize that as well. So remember from our previous work that a transformation is a function which maps from one vector space, in this case we'll call it space V, to a second vector space, which in this case we call space W. So every transformation is a function, and the only restriction is that the domain and the codomain, the input and output values of a transformation, are vectors. When we talked about transformations previously, we talked about transformations that would go from a Euclidean vector space to itself or between different Euclidean vector spaces. So we had transformations that took three-dimensional vectors and turned them into two-dimensional vectors. We had transformations that took two-dimensional vectors and turned them into five-dimensional vectors, and so on. Now, with our broader understanding of a vector space, we can have transformations that take polynomials and turn them into matrices, or take matrices and turn them into three-dimensional vectors, so on and so on. Again, this being a course in linear algebra, transformations in general are not the thing we care about. A transformation is called linear if and only if it preserves linear combinations. That is to say that the transformation acting on C1V1 plus C2V2 is C1 times the transformation of V1 plus C2 times the transformation of V2. And whenever you have a transformation that behaves like that, we call it a linear transformation. And linear transformations are the ones that we are going to study in this course. That's what makes this course linear algebra. So consider, for example, the transformation I'm calling D here, which maps from P4 to P3. We're going to define D as taking the function a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth, which is what a generic polynomial in the vector space P4 looks like. And it's going to spit out the resulting polynomial a1 plus 2a2x plus 3a3x squared plus 4a4x cubed. And if you stop and think about this transformation for just a few moments, you will hopefully recognize that this is a special case of the differentiation operator from calculus. If we wanted to take the derivative of a polynomial, we're going to end up with a new polynomial which is 1 degree lower. We call differentiation an operator because in the general sense in calculus, it takes a function and returns a function. And remember that an operator is a transformation that maps from a vector space to itself. We're not going to be too tied up in that. We're not going to worry about when that is happening in this course, but that is a little bit of vocabulary. And that's why the difference between calling it a transformation here and calling it an operator in calculus. I've mentioned before, if you're moving onward, you may eventually find your way towards a course with a title like functional analysis, where you take the ideas we've been talking about here and extend them onto infinite dimensional vector spaces, the set of all differentiable functions. If you just take your polynomials and continue them to infinity until you have a complete Maclaurin series, you can write any differentiable function in that way. And so the set of all differentiable functions is a vector space of infinite dimensions, and you can do all the same things. It's not that much more complicated, but there's a lot more theory behind it, which is why we're not going into it in any depth in this course. But while we're on the topic, I wanted to mention that that's what calculus is doing. That's what you are dealing with in calculus. We just don't call it that yet. But we know from our study of calculus that differentiation is linear. Let's prove it in the context of these polynomials. So to show that something is a linear transformation, we're going to need two polynomials. Let's call them f and g. And we're going to need two constants as well. I think I'll use p and q. So we're going to take our operator d on p times f plus q times g. And if we expand out p times f plus q times g, it's going to be difficult to fit on the screen, but I'll do my best. We have p times a naught plus p times a1 times x plus p times a2 times x squared plus p times a3 times x cubed plus p times a4 times x to the fourth. And we're going to have q times a naught plus q times a1. I'm sorry, these shouldn't be a's, these should be b's. Q times b naught plus q times b1 times x, q b2 x squared, q b3 x cubed, q b4 x to the fourth. And of course, all of the terms of this argument of the operator are real values, so we can use the commutative and associative and distributive properties of real numbers to rearrange this. And we have p a naught plus q b naught. We have p a1 plus q b1 times x I'm going to use dot, dot, dot because this pattern is just going to keep going until we end up with P A4 times Q B4 times x to the fourth. And that way I can fit everything on one line and it makes me a little bit happier. Now, following the rule. The rule of linear transformation D did nothing with the constant term. A naught disappeared, so this whole first term is going to disappear. It took the coefficient of x and made that the constant term. So we will have P A1 plus Q B1 as our constant term. Then we had 2 times the coefficient of the quadratic term, P A2 plus Q B2 times x. And we had 3 times the coefficient of our cubic term, P A3 plus Q B3 times x squared. And we had 4 times, it'll be P A4 plus Q B4 times x to the fourth. And I can, again, use the distributive rule, use the commutative and associative properties, use the distributive rule again, and regroup all of this. I'll do it in 2 lines, but I can get all of my terms that have p's in them together. Let's make that 3 over there look like a 3. I don't know what it looked like before. And let's get all of our terms with q's in them together. Before factoring out the p and factoring out the q, and recognizing that the stuff that's left in the parentheses is exactly my transformation D acting on the function f and my transformation D acting on the function g. And so we end up with that same linear combination after the transformation, which is exactly what it means for a transformation to be linear. There are several things that we did with transformations when we first saw them. One of the most powerful things that we observed is that if we have a basis for a vector space V is a set of vectors S, a subset of V. We'll call the vectors in this case U1, U2, down through to UN, such that span of S, which sometimes you see written literally span of S, sometimes with these angle brackets, but either way, that gets you back to set V. So remember what a span means. That means that we can write any vector V as C1 U1 plus C2 U2 plus all the way down to Cn Un. And the reason that the basis was so useful in the work of linear transformations, if T is linear, then T of V is equal to C1 times T of U1 plus C2 times T of U2 plus all the way down to Cn times T of Un. A linear transformation is defined completely by its action on a set of basis vectors for its domain. So again, if T is a linear transformation acting on vector space V, and this set of U vectors was a basis, we saw that if we know the transformation of T on all of the basis vectors, and we know how to write any other vector as a linear combination of those basis vectors, that we know what the transformation will be on every vector. That is incredibly powerful. For our purposes, we're going to use that very directly. We are going to look at a vector space. We are going to define a transformation on a basis for that vector space. And we know that by extension, that transformation will have to be linear. In the real world, in applications of linear algebra, this tends to go the other direction. You have a transformation, you know that it's linear, you start to investigate what it does, you develop the logic for its action on the basis, and now you know how to apply it on the rest of the vector space. But in this course, we don't have time to get into the details of how do we identify that we are looking at a linear transformation in the first place. We just want to know what to do once we have it. And so, sorry about that. I don't need a bright white screen. I just need a clear screen. So let's assume that we have a linear transformation T. In this case, I'm going to have T acting on the set of quadratic polynomials. Now, we can use the basis of quadratic polynomials. Every polynomial, every quadratic polynomial is a linear combination of 1x and x squared. So if we assume the properties of T on those basis vectors, T of 1 is 1, T of x is 1 plus x, T of x squared is 1 plus x squared. With that information, based on the theorem I just presented, this has to be a linear transformation. And if it is a linear transformation, we can evaluate it. So in particular, I would like you to evaluate the transformation T on the polynomial 3x squared plus 5x plus 8. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.